Electrochemical changes. Chapter 12. Oxidation, Reduction, Reactions. Up to this point, high school chemistry students have perhaps assumed that if a chemical equation can be written, then the reaction must occur. In this chapter, we will learn how to predict whether a reaction will indeed spontaneously proceed to products. It is useful in reviewing how to write ionic compounds, recalling that an ionic compound with a net charge of 0 is comprised of a cation and an equally but oppositely charged anion. Remember also that polyatomic ions listed in your data book are frequently used in ionic compounds. In Chemistry 20, you learn how to write net ionic equations by dissociating soluble ionic compounds into ions and removing spectator ions. Analyzing net ionic equations is important to seeing the movement of electrons between the reactants to form the products of an oxidation-reduction reaction. Chemists originally defined oxidation as any chemical reaction with molecular oxygen. An operational definition describes what something does. Magnesium burns very brightly, and the product of this reaction is magnesium oxide. Turning the equation into an ionic equation, it's easy to see how it is the movement of electrons that have influenced this reaction. The magnesium metal has lost 2 electrons to become the magnesium ion. A theoretical definition is one that attempts to explain why a phenomenon occurs. The theoretical definition of oxidation, then, is the loss of electrons. When metal is extracted from ore, the mass of the metal is less than the mined ore. Historically, a reduction in the amount of mass like this earned it the label reduction. Iron 3 oxide, or hematite, is reacted with carbon monoxide to form iron metal and carbon dioxide. The iron oxide ore is reduced to iron metal. Specifically, the iron ion is gaining 3 electrons to become iron metal. Reduction, then, can be defined as the gaining of electrons. To remember which term means losing electron and which term means gaining electrons, use this simple memory mnemonic. Oil rig. Oxidation is losing electrons. Reduction is gaining electrons. Reduction-oxidation reactions, or redox reactions for short, have an atom, ion, or molecule gain electrons that have been given away or lost by another atom, ion, or molecule. Redox reactions can fit into several reaction categories. Formation and decomposition reactions are often redox reactions. Combustion reactions are reactions with oxygen, so they're redox reactions. Single replacement reactions are redox reactions. This is a single replacement reaction representing a strip of zinc metal in a solution of copper 2 sulfate, as shown in this picture taken from your textbook. The nature of this reaction can be seen more clearly if the chemical equation shown here was rewritten as a net ionic equation. Recall from Chemistry 20 how to write net ionic equations. Dissociate all soluble ionic compounds, checking the solubility table in your data book. And then remove the spectator ions, that is, the ions not involved in the chemical reaction. In the equation shown here, the sulfate ion of the reactants turns up as a product, and so is not a contributor in the overall reaction. Our net ionic equation. From here, we can track the electrons. The zinc atoms are oxidized. They lose 2 electrons to become zinc ions. Every 2 electrons lost by the zinc atom is gained by the copper ion. The copper ion, therefore, is reduced to copper metal. If this were the case, then we would expect to see copper metal appearing as the reaction progresses. And as you can see, we do. The dark material adhering to the zinc strip is indeed copper metal. We can summarize the reactions of a redox reaction as follows. Zinc is oxidized, that is, it's losing electrons, causing the copper ion to reduce, that is, gain electrons. In other words, the zinc metal is the agent responsible for the copper ion's reduction. Counterintuitive though it sounds, the substance undergoing oxidation can also be called the reducing agent. Likewise, the copper ion is the agent responsible for the oxidation of zinc, and can also be called the oxidizing agent.